Hi. Hello, everyone. I'm going to be waiting a couple of minutes for other people to show up, but it's nice to sort of be here, and I'm excited to teach you this class. I hope your week is not going too badly. It's only Tuesday, so hopefully there's not been enough time for something to go particularly wrong. Hello again, Fatima. Nice to see you in the comments section. How long should we give it? Should we give it like another 90 seconds or so? Is there going to be practice questions? Yes. Yes, Wajiha or Wajiha? If you would like me to pronounce your name correctly, please send me some guidance. But yes, there are going to be practice questions. Hello, James. Hello, Kushi. Hello, Angelique. Hello, Jessie. Do I recognize your name, Angelique? Possibly. Yay! Oh, okay. Yay for Fatima. I'm so glad that actually happened because you were a bit unsure with your private Insta account. I'm going to have to say that today, actually, if we've got the same thing happening. What uni did I go to? I went to UCL, University College London, but that will be covered because I do like a hello, my name is Georgia, and this is all the things about me thing. Hi, KF. Hi, Pooja. All right. I think that we can probably get started because it's just about past, and we've got some lovely people here already. So I'm just going to share the presentation instead of my face. Dun, dun, dun. Right. So you should all be seeing a mass spec presentation. Yes, I said UCL. The syllabus is the same for CIE. Okay, so the exam boards that we're covering, why does the button not want to press? There we go. The exam board that we're covering, examples that we're covering are AQA, EdXL, and OCR. There's lots of crossover with CIE, but it's not going to be exactly the same, but it should still be very useful for you. But there will be like tiny details that will be slightly different, but it should still help. What did I study? We're literally going to get onto that in a second. So I'm going to just get started. So this is going to be a class on Mass Spectrometry, which is a year 12 module. This is the thing where I tell things about myself. So my name is Georgia. I'm head of chemistry here at SnapRevise, and I did sort of like an integrated bachelor's and master's in natural sciences, which is the degree that I always say you pick when you can't make decisions, because you get to do lots of bits and bobs with the sciences, but I mainly specialized in chemistry. So yes, so I've been sort of teaching and tutoring A-level chemistry for about 6 years now. So lots and lots of time to get used to all of the different syllabuses. And yeah, so hopefully I'll be able to help you lots. CIE is basically OCR for people who don't have English as a first language. I'm not sure that's quite right. It's international, but it's not too much about language. Yeah, 45 minutes to an hour is right. Cool. All right, let's move on. So just quick word on what these web classes are. They're not really detailed. They're not everything that you might ever need to know on this subject. They are key points. They're a recap. And because we're doing lots of different exam boards, I will say when we're sort of not covering something that one of the exam boards does, that we're doing sort of like general concepts and exam questions, exam techniques, and you have a chance to ask me questions. And for the next few weeks, they're free, which is nice, but they won't be free, or at least not all of them will be free from October 16th when we launch our SnapRevise 2.0, which is exciting. It has lots of cool things that I will tell you about at the end. But yes, so this is for free for now. At the end, as sort of Fatima said in the comments, so Fatima won the free account last time. If you want to have a chance of winning a free account with us this time round, you need to follow us on Insta and then share a picture of the web class to your story and tag us in it. do be aware if your Insta is a private account, it's not going to show up when you tag us. So if it's not on a public account, that might not work so well for you. And also there is a coupon code at the end of the web class for a discount, a really nice discount for all of our stuff. So stick around for that. That's how we keep you here. And also obviously my amazing teaching hopefully also keeps you here. But then that's also just like a little perk. Yes, so my lovely colleague has just said in the comments, if your account's on private on Insta, send a screenshot of the story to us on actual Insta, and then we'll know that you actually did it. But yes, keep that in mind. Yes, oh, cool. Yeah, sorry. I studied at UCL. Was that from before? Yes, AQA is suitable, but we're going to be going through that, Samiha, in a little bit. So yes, so what are we going to be covering? We're going to be covering how mass spec works. We're going to be covering how to calculate relative mass from your mass spectra and how to determine molecular structures from mass spectra. We are doing sort of the basics of time of flight under the understanding how mass spec works, but we're not going into like the fine details that specifically belong to time of flight mass spectrometry, which is just like one type of mass spec. We're also not going to be looking at anything to do with carbon-13 peaks, just because, again, another detail, you can learn that by yourself. It's kind of memorize-y, so we won't be doing that. Okay, so all good to get started for what we already know. And I've just seen Snooker Gaming say, do you believe that you're better or as good as tailored tutors? And then like, obviously I'm gonna say that I think that we are fabulous. I don't like to make comparisons because I think that different people give different things, but personally I would stay here if you were going to make a choice. Yes, but obviously like if you ask me, I'm really super biased because this is the thing that I do and I like craft it, especially for you. And then if I thought somebody else was better, I'd be doing what they were doing and not what I was doing. And I'm rambling, so we're gonna get on with what you guys should already know about mass spec, or about the sort of the details you need to know before you do mass spec. So I'm gonna need your help. I want someone in the comments to tell me what relative atomic mass is. So what is our like really good details of relative atomic mass? Definition: the average mass of one atom, 1/12 the mass of carbon-12. Yeah. Compared with, oh, wicked. So both Jaisal and Molly, yeah, you're totally right. So just a quick word. If you aren't engaging with the stuff that I'm asking out, the questions are a way to help you learn. So I want you to just sort of like, don't wait for other people to answer them. Even if you don't know the answer, have a think about what it could be, because you will remember things much better, I promise you. So relative atomic mass is the mass relative to carbon-12. You can also say that it's a relative to the 12th of the mass of carbon-12. It doesn't really matter, both are fine on the mark schemes. And you also need to say that it is a weighted average. So that's something that not everybody put in. Weighted is a super important word, which we covered last week, so I won't be covering this week, but make sure you add that in. So it's a weighted average of isotopic masses. Right, lovely. Does somebody want to tell me what an isotope is? Atoms of the same element with the same number of protons, but a different number of electrons. Not quite, Logan. Have another stab at it. So we've got Hamian. An isotope is the same atom having different neutron number. Kind of, you can't really call it the same atom if it's got a different number of neutrons though. So we've got Fatima saying an atom. I'm getting so many messages, I can't possibly read them all at the same time. Okay. Same element with a different number of neutrons. Kind of, like that's almost right, but I like to add in protons. So I'm going to go with KFs. It's got the same number of protons and electrons, but has a different number of neutrons. The electron bit does not matter because electrons, sort of, you can have almost any number of electrons. It's the same element. So an isotope, oopsie. is an atom with the same number of protons, but a different number of neutrons. Wicked. Okay, so thank you everyone who answered. I really appreciate it. Hi, ma'am. Ma'am. Am I ma'am? Am I ma'am as in like mom, or like ma'am as in like mum? Molecular mass is, anyone? What's molecular mass? What's the difference between molecular mass and relative atomic mass? Molecular mass is the mass of compound relative to atomic, kind of. Yeah, so no or no Peckham. The relative atomic masses of all the elements in the molecule added together. That's perfect. So thank you everyone. So the sum of the masses of all atoms in a molecule. And the last thing that we really need to know, yeah, Angelique, that's a good way of thinking of it. AR added all together to form MR. Yeah, perfect. Yeah, and an ion is a charged particle. Yeah, charged particle. Or so particle is a good catch-all because it could be an atom or a molecule. So yes, lovely. And no worries, Zane, you can be late to a web class because I can't see you. So it's all good. An ion is a charged atom or molecule. So ion is positively charged. So with GHA, it's not necessarily positively charged. It could be any charge. It could be negatively or positively charged, but it's charged. Okay, thank you everyone for replying. We're going to continue on with just sort of looking at some of the spec points. So I just want you guys to have a look at these just really quick. I'm not going to go through them, but these are, if you're on AQA or Edexcel, these are the things that we're covering. These are the points. So now that you are A-level students, it's really up to you to be making sure that everything on your specification is in your head. It's not your teacher's responsibility, it's yours. So I would sort of print these out and then tick them off as you know them. And when you're revising, do exactly the same thing. So OCR is coming up, don't worry. It's the next page. There you go, OCR. There you're right. You're okay, Jesse, Harry, and Sarah, and F. So many, but yes. And then this is the OCR. Points on the spec, same thing for you guys. Make sure you know everything on the list by the time you get to your exams. Yeah, so this is, why are you excited for this? I don't know, Sammy, because you are a science pro, because you're nerdy like me. Chemistry is exciting. Okay, let's continue. Right, what is mass spec? Okay, so mass spec is essentially what we use to measure the mass of things, hence the word mass. It can be used to measure the mass of elements and isotopes and molecules, and it sort of happens in a few steps. These are sort of like compressed steps. So you could sort of break down the acceleration into acceleration and flight, or detection into sort of like hitting the detector and then the computer doing its thing, but we've sort of like smushed it together. And I've put a little note on the bottom that AQA requires a lot more detail. So please do have a look in your textbook for that. Let's have a look. Okay, so does anyone know, we've just been talking about ions. So what does ionization mean? What is that? Is this time of flight? So Jess, this is the basics of time of flight, but it's not all the details of time of flight. So you need to be memorizing the details by yourself, but I'm giving you the concept. Yes, it's when something becomes an ion. So like what's being added or removed. Yes, just as I say it, Sarah says yes. So ionization is when you are sort of like either adding an electron or knocking one off. And in this case, you're knocking one off. So in mass spec, the first step is one or more electrons are knocked off the sample. So you put in a sample, you're like, I want to know what this element is. I want to know how much it weighs. So you put it in and you ionize the sample molecules to create some positive ions. So bonus points if someone can say what a positive ion is. What's it called? And yes, Jazel, so this, you can be using electron spray or electron bombardment. So this is one of those details I haven't added in. So like you could either be like literally like shooting electrons at the particle so that other electrons fly off. There's lots of different methods of ionization. So we're not going to be covering those in detail. So many cations. Yes. So we're going to be making some cations. Everybody, yes, everything that is cringy, great name. Yep, you're right. Harsh fear. Yep. Cool. So I'm going to put a little note on the bottom of this ionization that it may cause fragmentation. And we're going to be covering that in more detail in a bit. But fragmentation is essentially when the molecule just sort of falls apart. So if it's not just one atom and it's like a big molecule, shooting a bunch of electrons at it might make it break in half. So that's going to be really important later. So I will add that in. So this may also cause fragmentation. Cool. So the next step, once we have our ions, we essentially accelerate them. So what if we've got something that's positively charged, what do you think is a good way of getting it to move somewhere else? Anyone? Positive charged ions are attracted to a negatively charged plate, causing them to speed up as they travel towards the negative plate. Oh, perfect. Yes. So essentially, we've got something positively charged. If you use something negatively charged, everything's going to rush towards that. So that's our acceleration. So negatively charged plate. Perfect. So many great answers. Yeah, wicked. So acceleration, the ions are accelerated by attraction to a, and I'm really lazy, people. So when I write negative, I'd like literally draw the minus sign and put a VE, like negative at the end, because I'm lazy. Don't do that in your exam. Do as I say, not as I do. You will find out sooner or later that scientists are all very lazy, especially when they're writing things down. Detection. So we've accelerated our ions. We've sort of like, we've knocked off some electrons. We've got them charged. That means that we can drag them towards a negative plate. And it's this acceleration that we're detecting, right? So will this be saved? If Debs, you mean, will you be able to see this after? Yes, you will. It's going to just sit on YouTube, so you can watch it later again. So Jazel says ions are detected by mass. Lighter ions arrive first. Yes. So like this is, I was just about to ask that question. I was going to ask, what do you think will arrive first? What do you think is going to accelerate faster? Something light or something heavy? But somebody already said it. So deflection, everyone's just like dropping in a bunch of key words. You did this light. Yes, thank you, Fatima, Hazel. Smaller and more charged. Yes. So the first thing is the lighter atoms or ions, sorry. The second thing is that the more charged they are, the more they're going to be attracted to the negative plate, right? So anything small, anything really charged, that's going to get there first. And this is how we're measuring mass. So it's the time it takes to get to the detector sort of divided by the charge, so that we sort of rule out the fact that it's just got more of a charge, will tell us how much mass it has. So under detection, I'm going to write the lighter particles. Ooh, that's an O, not an M. Move faster. So are detected first. More charged particles, oops, also move faster. Ah, Debs, I love organic because that was my specialism when I was doing my undergrad bit of my degree. Pooja, I am going to cover how to analyze mass over charge ratio, but I'm not going to cover calculating the actual mass over charge ratio, but it's pretty self-explanatory because it's literally mass over charge. But we are going to be covering analyzing data from Mass Spec. Okay, so this is the basics of how Mass Spec works. Again, if you're doing time of flight, you need more details than this. You need to be covering electron spray and electron in your ionization category and different methods of, but it's memorizing. It's not difficult to understand. So that's why we're not covering it. So you can have a go. Okay, moving on. I have a question. So that 1,000 subs with no video, that is something that you need to be checking on your spec. So this is something you need to take responsibility for yourself, I'm afraid, making sure that all of the details are there. Again, this is meant for key points and helping you guys understand the concepts and answer exam questions, not giving you every little detail. And I'm going to stop saying that now because I've said it lots of times. But yes, so find your details. Cool. So how do we calculate relative isotopic mass using our mass spectra? So essentially, if you guys were here in my last lesson, we talked a lot about relative abundances, meaning sort of like how often does any given isotope show up in a sample? So let's say you had some like ash, which is mainly carbon, right? And you wanted to know sort of how much carbon-13 is in there, how much carbon-12 is in there, how much carbon-14. You would shove your sample into a mass spectrometer and you would calculate using your relative abundance and the mass to charge ratio. So you guys should be able to remember, if you were here last week, the formula. How do we calculate relative atomic mass? What's the formula? We're having lots of lag. Try refreshing your page. Oh, okay, so we've got mass times relative abundance over 100. Yes, Logan. Yep, and then we've also got Jess and Priya killing it with the actual calculations. So I will just write it down. So we're doing mass over abundance times 100 is right. And in this case, it will be, we've got 75 here, and the mass charge ratio is 35. So we're timesing those together. And then we've got 25 as the abundance, and we've got 37. And we divide that by 100. Yeah, wicked. Not much lag anymore. Excellent. Thank you for letting me know. So that should be, if you shove that in your calculators, that should be 35.5. And yes, Harshvir, we will be covering structure determination. That's the last topic. Okay, so moving on. How are you feeling about that? How is that? Is that all making sense? So I know that this just has emojis and numbers. If it's straightforward, you can go ahead and do emojis. If something's confusing, please actually tell me what is confusing, or I cannot help you because I need to know what the specific thing is. Straightforward, straightforward. Yeah, people are getting it. Wicked. I'm so glad. Cool. Perfect. Yeah. All right. Everyone's happy. 4 Hallian. That is not a helpful. That is really not a helpful response. If there's something spectrometry means. Oh, so spectrometry means essentially like creating a spectrum. So this being the spectrum. So the mass bit, creating a spectrum for mass. But yes, we're gonna go ahead and do our exam question then, if everybody is good. Right, so here we've got the copper used to make a batch of coins is analyzed by mass spec. The mass spectrum is shown below. calculate relative atomic mass of copper used to make the coins. Give your answer to 2 decimal places. So I know that lots of people just sort of chuck this in really, really quickly. Amir is confused about calculating relative atomic mass and molecular mass. So, okay, so that was kind of last week, but so what I'm going to do is you guys are going to look at this and you're going to be working out the relative atomic mass. You're not going to be putting in the answer yet. You're going to wait until I say put in the answer so that other people have the chance to actually do it. And while you're doing that, I'm going to answer Amir's question. Debs, I will be doing organic, but later on in the year, much later on in the year, I think. Amir, relative atomic mass is the calculation for, like, is this calculation for this exam question, essentially when you're timesing abundance by mass and dividing it by 100. Molecular mass is when you're just adding up the relative atomic mass of all of the atoms in the molecule. Guys, I like properly said, don't write the answers in there. Nobody listens to me when I say that. I don't know. Don't write it in there yet. No, nobody's listening. Okay, well then I will go ahead and start writing the working. Your face is, I don't know what that's coming in the way of the questions. My face is coming in the way of the, oh, it is, isn't it? I don't know how to move that. Hang on. Give me 1 second. That should be better. I'm really sorry. It's a different lesson. That was last week. So what I suggest you do is go take a look at last week's video for year 12 because it covers it in that, but I can't keep covering things from before or we won't get to cover what we're covering today. So what I'm going to do is give you guys the working because all of the people that said 63.62 were completely right. So this is the working you need to have put in to get all of your marks. And I have, so it should be 69.17 times 63 plus 30.83 times 65 divided by 100. And that should give you 63.62. Dia, MZ is mass to charge ratio. So if you remember when we were covering how it works, we said that 2 things make something accelerate faster toward the detector: the weight of the ions and the the mass of the ions and the charge. So what we do is sort of divide by charge to make sure it's not just because more electrons have been knocked off, it's actually got lighter mass. So it's MZ is mass to charge ratio. Okay, so the next question, bromine has 2 isotopes with relative atomic masses 79 and 81. Which of the following values for mass to charge ratio could correspond to the peak in the mass spectrum of bromine? You should assume ions detected have a single positive charge. So what? Okay, so we've got lots of different, it should be about an hour coming in. Lots of answers. So everybody that said that 63.62 for the other question was right. Anyone for the bromine question? You don't get the bromine question. KF, what don't you get? Okay, so we've got a couple of people saying, so we don't get the question. Okay, so I'm going to break it down a little bit. And we have some wrong answers. Cool. So the most important thing to be thinking about is that it says which of the following values for mass charge ratio could correspond to the peak in the mass spectrum of bromine Br2. That's the big clue there, right? We've got Br2. So that means we've got 2 bromines, right? And if the isotopic masses could be either 79 or 81, it has to either be something that would be 79 plus 79. So that's 1 bromine and another bromine. It could either be something that was 79 plus 81, or it could be something that was 81 plus 81, right? So 79 plus 79, someone want to tell me what that is? Anyone do maths for me? Yes, thank you. So 158, so that's not an option. What about 79 plus 81? Yes, anything? Anyone? 79 plus 81, 160. Yeah, and then 81 plus 81. I'm just going to do it for you, 162. So out of all the options here, the only one that's on this list is 160, right? So it's got to be D. Is that making sense to everyone? So the sort of like the main bit in that question that I think might have been throwing everybody off was that we've not got any abundances here, because it's not asking you to calculate the relative atomic mass. It's saying what will be the mass spectrum for BR2. Yeah, got it? Got it? Yeah. People are getting it. Everyone kept putting and got me confused. Yeah, I mean, like, that's why it's really important to sort of like be thinking about the question yourself and not sort of letting other people guide you, because you may have had the answer and then you could have helped us all. Are there any websites to get these practice questions from? So these are from old exam papers, and there are a couple of websites that have like sort of like a conglomerate sort of like it shoves all the topic questions together. There are a few called, I think one of them is called Save My Exams. Another one's called Maths and Physics Tutor. But then, of course, we also have a bunch of exam questions that we make so that if you run out of the actual old ones, then you still have ones to do. So that's on our website. But yes, we've got to move on. Amit, I keep saying you've got to watch the video from last week. I can't go over things from last week again because we will run out of time. Part 2. So we're going to be talking about how to identify molecules. So the most important thing about molecule identification is the fragmentation that I mentioned earlier. So if we think back to how mass spec actually works, we know that it gets bombarded, right? We know that we've got like a bunch of electrons flying at our sample so that we can ionize it, so we can knock off electrons. And sometimes that breaks up molecules into pieces. And that is actually really helpful because it means that we have lots of different peaks. And we're going to be talking about what their use is in a little bit. But the first thing we're going to do is calculate the relative molecular mass. So when they fragment, we've got like all of these sort of other peaks here, and we're going to ignore them if we want the relative molecular mass, right? So Fatima is saying that you don't understand mass to charge ratio. So mass to charge ratio is literally just, it's how the detector converts the sort of time of flight across the mass spectrometer into a value that ignores the charge. So because charged ions move faster, you don't want the detector assuming that they're lighter particles, right? So it's literally over the charge so that you cancel out any sort of charge relationships. So as I was saying, because we've got this fragmentation, that's where we get all of these random other peaks from. So the only peak you want to look at when you're calculating relative molecular mass is the last peak, because that's the one that's only had an electron knocked off and it hasn't been broken up into any pieces. So this, yep. So I can see lots of people saying 46. So what does it mean by peak? Peaks are just these lines. So they're in red, and unhelpfully my pen isn't also in red. So these are peaks. That's a peak. So this last peak is the important one, and it's the M+ peak, meaning it's the whole molecule that's positively charged rather than a fragment. Yeah. So we should have 46, and we know that because if we were to actually calculate it the way that we calculate relative atomic mass, we would do 2 times 12 because we've got 2 carbons and carbon is 12. We would do 16 times 1 because we've got 1 oxygen, and oxygen's relative atomic mass is 16. And then we would add how many hydrogens? 1, 2, 3, 4, 5, 6. And that would also give us 46. Why is there no M+1 peak? There is, it's right there, the M+ peak. Why don't you add them together? We do add them together. If you sort of, it is the molecular. So I was confused. I thought the highest peak was the molecular relative. It is the relative molecular mass. So, oh, the highest peak. No, okay. So along your y-axis, Jess, that's abundance. It's not, so the mass to charge ratio is the thing that's going to tell you the mass. So it's not the highest, but the peak with the highest mass to charge ratio. So not like literally the highest vertically, but the one with the highest x-axis value. Why is that the molecule peak? Because it's the heaviest. Yes. So as I said, when this molecule goes in to be ionized, it sometimes the ionization process, so you could be like bombarding it with lots of electrons, might chop the molecule in half, right? Instead of just knocking off an electron. So that sort of half a molecule will also have a peak, as well as the ones that didn't get broken in half. So the peak with the highest mass to charge ratio value is the whole molecule. That's why. Does that all make sense? What is the most abundant peak? Is it important? Yes, Fatima, it is important, because if you remember, for this question, that's how we worked out what the relative atomic mass is, right? We looked at the abundance times the mass to charge ratio. So the abundance is important if you want to know how often something is showing up. No, I don't get it. What are we not getting, people? How did I do the calculation? So this calculation is just how you calculate relative molecular mass, where I'm literally just adding up the masses of all the molecules. But we didn't need to do that. I was just doing that to illustrate the fact that this M plus peak is the same relative atomic mass that you would get if you were doing the calculation. So I did it by adding up. So I had 2 carbons, and carbon's relative atomic mass is 12. So I did 12 times the 2, and then we've only got 1 oxygen. So that's 16. And then we've got 1, 2, 3, 4, 5, 6 hydrogens. So that's plus another 6. And that gives you the same value as the M plus peak, which is 46. Why is the M plus peak not the highest peak? So have a look at the X and Y axis. So it's your x-axis, the one that runs horizontally, that is your mass to charge ratio. So it's the highest mass to charge ratio, not the highest vertical peak, because your y-axis is abundance. It's how much of that thing there is, not how heavy it is, not how massive it is. So mass doesn't change is your point. No, that's not my point. It's not that mass doesn't change. It's just, I'm just demonstrating that you can either calculate the relative molecular mass from the relative atomic masses. And if you want to check if your mass spec has got the thing that you think that you had, then you would calculate it, and then you would look at the mass spec M plus peak. I don't get how you do it through the graph. So Ira, through the graph, the M plus peak, so the peak with the largest MZ, the largest mass to charge ratio, is the one furthest to the right, right? Because here we've got 10, 20, 30, 40, 50. So the largest mass to charge ratio is the molecular mass. So the aliens are coming. I did say at the beginning, I'm not going to cover anything to do with carbon-13 because it doesn't come up in all of the exam boards that we're covering. It only comes up in one. Yes, yes, Fatima. So Fatima's just said, so the peak that's furthest along the x-axis is the actual mass, and the other peaks are masses of little fragments that came off the molecule during ionization. That is exactly right. So why are there 5 peaks? So what is SnapRevise 2.0? Which exam board does carbon-13 come in? We've got lots and lots and lots of questions. If my colleague could deal with some of the questions, that would be great, because I'm not going to have enough time to cover them all. Oh, look, other people have jumped in. So AQA. Why are there 5 peaks? All right, so what I'm going to do is move on to the next slide, because that should make it really clear about why there are 5 peaks. if people are confused about why there are other peaks and not just one. But the last thing I want to say about this slide is if you're trying to calculate the relative molecular mass, the last peak to the furthest to the right with the highest MZ value will do that for you. And we will come back, I promise, because the next slide should make things make more sense, because we're going to be talking about fragmentation really specifically. And I really wish I could change the color of my pen for this one. So Jess, we're going to be doing that now. So fragmentation is what happens inside your chamber when you're ionizing your atom or your sample. Sometimes what happens is instead of just an electron flying off, the whole thing breaks in half. So this, I don't want you guys to look at this one for a second. Ignore that one for a sec. Just look at this molecule here, and this is ethanol, right? So what we have here is the mass spectrum for ethanol. And as we said in the last slide, this peak here is the peak for the whole molecule. But what happens is in the chamber is that the molecule ends up breaking apart. So the first kind of fragment, one of the small fragments we could have is we could have just this bit. It could have broken up so that we've got just the CH3 part. We've got the methyl. You call that a methyl group. So just this is one carbon, which has a weight of 12, and it's 3 hydrogens, which has a mass, of 3. So that would give us, just this fragment here, would give us 15 in our mass to charge ratio. And we do, cricket ray, yes, it does cause fragmentation. And we do have a peak there. We've got a peak at 15 that corresponds to just this methyl group, right? So fragmentation's happened, we have a methyl group on its own, and it's only got a mass of 15, and that is why we have a peak there for that. Can I see some sort of response? Does that, just that bit make sense? The fact that we've got a fragment here and it's got a peak at 15. Can I see some emoji feedback? Yes, so Ira says yes. Yes, Esther says yes, no. So if it's a no, you're going to have to sort of try to help me out as to why. Yes, so we've got mainly yes. So I'm going to like rush sort of through what we're talking about. So I want you to imagine that this, if you're confused, this molecule is like literally being shot at by like tiny little electrons that sort of bump into it. And that might crash into it and like literally chop it in half, right? So if it's chopped in half and you've just got this carbon, this hydrogen, this hydrogen, and this hydrogen, the mass is not going to be the total mass. It's just going to be the mass of that bit, right? So that's 1 carbon, which is 12, and 3 hydrogens, which is 3. So you'll get a peak at 15. So that's the first sort of peak, first little peak that you can have. Is that when it loses an electron? Yes, it is when it loses an electron. So it could either just lose 1 electron from the edge, or it could lose an electron when it gets chopped in half. So anything that it's detecting has to be an ion, otherwise it wouldn't have accelerated. So the next peak is going to be this fragment. So in some situations, the OH will get chopped off, and oxygen has a weight of 16 and hydrogen has a mass of 1. So we should have another peak at 17, which we do. So that peak here is for the OH. So I'm going to start writing these in. So the 15 peak should be for a CH3, and the 17 peak should be for OH. So Mitzi, because there's so many, keep in mind that if you're putting in a sample, even if the sample weighs a gram, you're going to have like billions of actual molecules. So like some of them are going to break off at the CH3, and some of them are going to break off at the OH, and some of them are going to break down the middle. They'll all break off in different ways. So that's the first bit. That's sort of our OH peak. So we've got another peak here, and that peak is probably this fragment. So the next biggest fragment you can get, which is 2 carbons. So that's 12 plus 12, and it's 1, 2, 3, 4, 5 hydrogens, which gives us 29. Is my brain working? Yes, it is. And we do have a peak at 29. And that refers to this thing here, which is C2H5. So it refers to that fragment. Do we need to know where they break into fragments? Yes, Emily, but you can essentially just figure that out by chopping up the molecule in any way that it can be. Usually you don't get like hydrogens just being chopped off by themselves, but you do get any sort of like large chunk of the molecule. You should have all of those on there. So far we've had this, we've had this, and we've had this, and there's sort of only one real other option for how it's going to break up, and it should be if this end broke off by itself. So if you had 1 carbon, 1 oxygen, and 3 hydrogens, and that should give us a value of 31. Will they give us the graph in the exam? Yes, or they might give you a list of values, but either way you'll have the values. So this should be 31, and that's a COH3. Does that make sense? Can I see some emoji feedback? Is the fragmentation making sense? Yes. So yes, we've got some yeses. Yes, yes, yes. Okay. Wicked. All right. This makes me happy. Okay. So I told you to ignore this molecule here at the beginning because I didn't want you confusing what I was talking about. We're now going to talk about this molecule because if you notice, it's the same molecule in terms of how many carbons there are. So this ethanol here is a C2 because there's two carbons, 1, 2, 3, 4, 5, 6, 6 hydrogens and an oxygen. And if we do the same, we count for this molecule, we've got another C2, we've got 1, 2, 3, 4, 5, 6 hydrogens again, and 1 oxygen. So if we were just looking at the M+ peak, it would look like it was the same molecule. So even though they're different molecules, even though this one is ethanol and this one is an ether, our mass spec wouldn't be able to tell the difference between the two. It's the fragmentation that tells us whether it's ethanol or ether, right? Because ether will have different fragmentation patterns than ethanol. So in your exam, you may be asked to tell the difference between two molecules like ether and ethanol. Yes, yay! People are getting it. This good, because this is quite like a tricky topic, and I know that some people have a bit of trouble. So in terms of abundances for when you're looking at fragmentation, it's just essentially like which ones are most likely to be chopped off when they're bombarded by electrons. It doesn't really have any meaning past that, especially not for you guys. So you're most important if you're looking at molecular weight rather than relative isotopic or relative atomic mass, you just ignore the relative abundance. Don't even look at it. Don't look at the height of the peaks. Just look at the mass to charge ratio. That is the most important thing. Where is it on the mass to charge ratio line? Oh, yay, Fatima. I'm so glad that it is all clicking. Should we go from left to right and then start assembling the compound? It really doesn't matter. I did it that way. I went from left to right just because it's just more methodical. All you need to do really is just start chopping up your atom and looking for the peaks that would make sense for that part of the atom. Like you could have started at this end, or you could have started just, oh, that's not even like a good fragment, is it? Or you could have just done that first. It doesn't really matter. Just chop it up in all of the ways you can think of, apart from chopping off hydrogens, because that doesn't tend to happen with the electron bombardment. Hydrogen's really teeny tiny, so the chances of an electron just hitting the hydrogen is so slim. That's why you don't really see it. Okay, I will chop. Yes, chop away. Can I explain again the COH3? Yes, I can. So COH3 is this bit here. It's this carbon, this hydrogen, this oxygen, this hydrogen. So that's, if you count, that's 3 hydrogens because each hydrogen's mass is 1. We've got 1 oxygen, 16, and 1 carbon, which is 12. AQA. Fragmentation should be an AQA. So fragmentation should be everywhere. It depends. The questions might be harder in some exam boards, but I tend not to include things that aren't sort of everywhere. Right, lovely people. I am going to move on. So again, we're not going to be talking about specific types of ionization because that's memorizing and you guys can do that yourself. You can look at the textbook. We're only doing things that are like conceptual and hard to understand. Why is abundance so long? It's just random. It just depends what's most stable. And I'm gonna move on because I obviously talk too much and this is why my lessons overrun. But yes. Ivana, it's just a probability thing. If you're like bashing electrons at things, like it's not, the likelihood is it's going to break it in half rather than just knock off one tiny electron, right? It's just probability that you would have the most of something that's just broken in half. Okay, so I already asked you how you were feeling, so we're going to skip this bit. And we're going to move on to the exam question. So the first one should be relatively simple. We want to know what the molecular ion is. So remember the molecular ion is your M+ peak. Will they make you draw one? No, probably not. Drawing one's not that useful. So do people just want to chuck in which one is the molecular ion peak? Yeah, we've got a few correct ones. Yes. Yes, it's got to be the one with the largest mass to charge ratio because, of course, that's the one that hasn't been fragmented. So it's got to be the whole molecule. So the answer to that one is 256. So the next question is, suggest a formula for this molecule of sulfur. So this one is a little bit trickier. And I want you guys to think about if it's just sulfur, so it's telling us that there's nothing else in there, there's no other element. So all of the fragments have to refer to sort of like a string of sulfurs. So does anyone want to take a stab at, if we know that we've just got sulfurs, we've got some number of sulfur atoms in a row, what could the peaks be telling us about how many sulfurs there are? So we've only got two answers in there, so I'm gonna sort of let you guys. We're getting a lot of correct answers. So there are 8 sulfurs, right? Because if we had 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Yes, just making sure I can count. If you have 8 in a row, you're going to get 8 peaks because it could break off there. It could break off at the first sulfur. So then you would just have 1 sulfur. It could break off there. And then you would have 2 sulfurs. It could break off here. And then you would have 3 sulfurs. You could break off here. And then you would have 4 and so on and so on. So that, oops, that's not an S. That gives us S8. Mitzi, does that make sense? Yeah, so you're literally counting the peaks. Can you do, you can. Sorry, I didn't realize people were asking, can you do 256 divided by 32.1? Yeah, technically, you should be able to. Because that would give you 8 anyway. So either way is fine. You can count the peaks, or you can assume that the first one is just one single sulfur and divide the molecular ion by that. Either method is all good with me. Yeah, if you stop looking at abundance, it makes things a hell of a lot easier. Don't look at abundance unless you're trying to calculate relative isotopic mass. Does it work all the time? It works if you've got one single element. If it's saying that it's one thing and it's not multiple different elements, like it's not like CO2, it's not like C3H5O something, then it's fine to just count them. But this is a really specific case. Cool. So the last question, what is the formula for the fragment with the mass to charge ratio of 128? No, you do not ignore the small peaks. You need all the peaks. All the peaks mean something. Ignore the height of the peaks unless you're calculating relative isotopic mass. Yes, it does. Yeah, sorry, I should have said what it does. Yes, Pael, each peak does represent the different ways it can fragment when it's being bombarded during ionization. And we're getting a lot of S4s. Yes, so we know that one of our sulfurs must weigh or must have a mass of 32. So we do 128 divided by the smallest one, which gives us 4. So we've got S4, but you guys all would have lost your mark. Tell me why. So I'm going to put in S4 here, but we're missing something. What are we missing? It's not just 4. No, it's not that it's a decimal. Yeah. Yes, Hazel. Yes, Hazel. Yes, Mr. Jim Karen. Yes, yep. So it says it here, it's an ion, right? It's not an atom, it's an ion. And we know that it's got to be charged. We know that it's got to be positively charged because that is how mass spec works. You knock off an electron so that you can accelerate the ion towards a negative plate. So it has to be positive, and you will not get your marks unless you put a positive charge on there. So be really careful about that. So that's why it's so important to read the question super carefully. Make sure you've got your charge. So all ions in mass spec are positive. Yes. You may get a situation where one of them is negative, but in that case, it wouldn't accelerate towards the negative plate. It would be repelled, and then it wouldn't be detected. So even if negative ions existed, they would not be detected by the mass spectrometer. So they're always positive. Wicked. All right, I've got another exam question for you because I'm a cruel human. Right, so which of the following mass to charge ratios for singly charged ions would be present in the mass spec of propanal, but not propanone? So this is a mean one, but I'm gonna draw it for you. So it gives propanal as CH3. Actually, I'm going to do it their way because if I don't, it's going to be a bit confusing. I've gone HFR8. I've gone over how to calculate relative isotopic mass, and that's where it comes under. So yes, but not specifically bromine and chlorine. I think it was bromine. I think it was chlorine in the example, but I didn't say that it was chlorine. So I'm going to draw you propanal. So we've got a CH3, a CH2, a CH, and an O. And we've got propanone, which is a CH3, a CO, and then another CH3. So in this case, we're looking for which fragment is going to be in this one, but not this one. And so the thing that you cannot get, what can't you get in this one compared to this one? Anyone? So looking at the molecule, not looking at the number, what part of that molecule is only in the top one? So both have a double bond. Yeah, so there's no CH2 in the bottom one. So thank you, JDP19. There's no CH2 in the bottom one, but that's not on there because C is a 12 plus 2, oops, is 14, and we don't have 14 as an option, but you are totally right. So CH2 is not the thing we're looking for. Hugo, you're totally right. So CHO is another thing that is not in propanone, but is in propanal because the propanone doesn't have an H on that oxygen group. So in this case, we've got 12 plus 16 plus 1, which should give us what? No one? This should. So what would that give us? 29. Yeah. And 29 is on there. So the answer is B. Lovely. Everyone did fabulously. So let's do another practice run of these. Right. So 2 ketones. CH3CO, CH2CH2, CH3, and the other one, because I'm not reading that out again, both have a molecular mass of 86, which peak due to fragmentation into single charged ions would you expect to be present in the mass spectrum of one, but not the other. So Hamian doesn't understand. Hamian, the second question is kind of the same one as the first one. So it might be able to help. So with these two ketones, they're going to fragment in very similar ways because they're very similar. So I'm just going to sort of do it a bit bigger so that we can see the difference. So you can do this in your exam, you can write them out, and it might help you. So we've got these two, and we want to know from the fragments what kind of fragment could be in, for example, the top one but not the bottom one. So does someone want to sort of like say which? So Logan says CH3, CH2, CH2 can only be in the top one, and yes, you're right. So this fragment does not exist in the bottom one, right? Because all you have in the bottom one is CH3, CH2, and CH2, CH3. You can't have that long chain. So that would be 12 times 3, because there's 3 carbons, plus 1, 2, 3, 5, 7, which is 36 plus 7, which is 43, which is on our list. So that's our answer. How do we know if a molecule has a double bond involved if it's only been given the structural formula? So you don't need to know, right? Because it tells you, the only reason I've drawn it out is just so I can sort of circle things more easily. You could write it out like they do. You could write CO, CH2, CH2, CH3. But Cricket Ray, once you've done your whole A-level course, you will study ketones, and you'll know that ketones have a double bond. And you'll also know that things that end in al are something called aldehydes, and something called one is something called ketones, and you'll know what they look like. But I've literally just drawn them out to make it easier to answer the question. But I could have just been like, this bit here is different from this bit, but that's just harder to see. Can there be multiple spots which will give you the same answer? Yes, so there are multiple fragments that would only exist in the top one versus the bottom one. So you're literally just going to have to work them out until you get something that's on the A, B, C, D list. How do you know what shouldn't be present in the mass spectrum? So if you look at the molecule, you should be able to tell which fragments will exist in one but not the other. For example, this, so the one that is the answer, is this long bit here, and the bottom molecule does not have a CH2, CH2, CH3 part. You can see it in the molecule, and you can see it in the actual question. So it doesn't have a CH2, CH2, CH3. It only has a CH2, CH2, C. Will these types of questions always be in A, B, C, D? They will be if you don't have a graph. So if they've given you a graph and they've given you like the molecule itself, then they have to give you the A, B, C, D. So I wouldn't worry about that. Is this high resolution or low resolution mass spec? This is relatively low resolution, because we're using it for molecules and not for isotopes. I've deleted that bit, but yes. So CH3CO would have also been the case, but it's not on the list. But yes, yeah, we're right. We're telling the difference really well. And so you don't need to know that, Fatima. That's not important. So I'm not going to go over that because I am like just about on time. So I'm going to like rush through so you guys can ask me some questions. And I promised myself I would try to be more on time today. So we're gonna move on. Cool. So you guys should understand how mass spec works. So that's the ionization, acceleration, detection. So that bit, understanding that all works. You should be able to calculate relative masses. So that's when you do look at the abundance and you times it by the mass to charge ratio and you divide by 100. And you should be able to determine molecular structures So that's all the fragmentation. That's the stuff that we just did. Yes, you can cricket ray. Yes, you can, as long as it's related to this topic. If it's not related, then no. Right, so before the questions happen, what we're going to do is I'm going to show you around SnapRevise, because I would be remiss in my duties if I did not tell you all about our wonderful things. So the SnapRevise 2.0, this whole thing, this web class is going to be part of that. So it's free for now, but it won't be free forever. There'll be like a few free sessions, like probably on the weekends, but most of them will be part of SnapRevise 2.0. So if you would like to keep me around and a bunch of other really cool stuff, then that will be the way to do it. So if you already have SnapRevise, what you'll get when SnapRevise 2.0 comes out is the basic package. Thank you guys for coming, for everybody that's saying thank you. But if you want the pro, or if you want the ultimate, you get me, and you also get me throughout the week, so you can ask random questions that you're confused about in sort of like drop-in support and like a chat. The prices will be out soon, Ira. But yes, but you're going to get a discount in like a second. So we have more free web classes. So do set your reminders. So if you go to our YouTube page, there's like a live stream bit. Is it reasonable? I think it's going to be reasonable, but we don't have the exact pricing yet. So that will be for you to decide with your budgeting restraints. Yes, so please set a reminder for the next one. The next Year 12 one is next week, Tuesday. All the Year 12 chemistry is on Tuesdays, and all of the Year 13 chemistry is on Thursdays at same time, 6:30. So do have a look at that for me. And here is your beautiful code. So if you would like 40% off, I would, use the code, and essentially you get sort of the SnapRevise that we have now. And when SnapRevise 2.0 comes out, you will automatically be upgraded. Using this discount will make it cheaper than sort of doing it on October the 16th. So if you want the cheap version, do it now, even if you're going to upgrade. If you already have SnapRevise, so my colleague will answer other questions. Yes, and the free account from the Insta competition goes to Winnie's a Foodie. So there you go, you get SnapRevise all for free. Yes, and now I will answer your questions. So if you have any questions about what we've done so far, any of the exam questions you want me to go back over, we've got a little bit of time for me to do that with you guys. We will be starting physics, but it's just not started yet. Does the code need to be used tonight? Yes, it does. That code stops working at midnight. So Cricket Ray says the relative atomic mass. I should be writing some of this down before it disappears. You're welcome, Melanie. I'm so glad I could help. So we're looking for, we've got, I'm gonna have to write this down. So we've got relative, I should just write. We've got the relative atomic mass of silicone is 28.109, and it has 3 isotopes, Si28, Si29, and Si30. And we've got Si28 has an abundance of 92.2. Find the percentage composition of Si29 in silicone. Is there not? Cricket Ray, is there not like one other piece of information? Because I feel like there should be a feel like we need one more abundance. Can you double check, Cricket Ray, if there's an abundance missing? Just, you might need to solve it algebraically. Okay, so what I'm going to do is attempt to start it and hope for the best. So we're going to do 28 times 20. So remember, it's abundance times mass is equal to the relative atomic mass, which is why I feel like it's not going to work out. But this is how you would start it. So you would do, so we've got our first mass, which is silicon 28 times 92.2. And you would add 29 times, let's say, call it X, because we have an unknown, right? We have the unknown for silicon 29, which is X. But the reason that I'm saying that I feel like there's a piece of information missing is because we've got silicon 30 here, which is another unknown, which means when you have two unknowns in an equation, essentially you need two equations. That's when you use simultaneous equations. So we've got two unknowns. So we can't actually work out X and Y. We could work out X if we had Y, but right now there's not enough information here. So I'm wondering if you missed something. Yes, you could do it in terms of Y. Yeah, you can do it in terms of Y or in terms of X, but you can't find a number. You can rearrange it and say that Y equals something X or X equals something Y, but you can't work out what both Y and X are. And it says find the percentage composition by mass of silicon 29. So you can't do that unless you're going to leave a Y in there. Ah, Hazel. Oh my gosh. So Hazel has been super helpful because, oops, you're right. You're totally right. So because we know that it adds to 100, thank you, Hazel. 92.2 plus X plus Y has to equal 100, which also means that 92 point, is it 92.2? Yes, it is. 92.2 plus X plus 100 minus 92.2 plus X should equal Y. So that is very, very helpful. So we're going to do 30 times 92.2 minus X. Yes, you are beautiful, beautiful people. Obviously, my brain is not that good. So I'm going to be using my phone as a calculator. So I'm going to get rid of lots of our numbers. So if we do the 28 times 92.2, we should have 2581.6. And then we have 29x. And then we have 30 times 92.2, which is, oops, I've forgotten 100. Yes, I did, Jazel. I forgot 100. You guys are perfect. And this is a really good example of the fact that teachers do also make mistakes. So when you make mistakes, hopefully that makes you feel a little bit less bad. Okay, so we're going to be doing 30 times 92.2, which gives us 2766. And then we should also have minus 30x is equal to 28.109. And then we collect together our 29x and our 30x. So that I'm going to collect together those numbers first as well. So you guys should be doing this along with me, because if I'm putting this in my phone calculator wrong, then someone is going to need to tell me. So I'm writing it up here because I've run out of space. So we should have 5347.6. And then I'm going to collect these together as minus x is equal to 28.109. 109. So this is, where did the 100 go? You guys are right. It went, so the 100 went, yeah, it did disappear. Yeah. See, I'm just having one of those days, aren't I? I'm having one of those days where my brain is just not wanting to function. Sorry, there should be 100 in there. There should definitely be 100 in there. And that is why my working was getting like super dodgy. So I'm going to be more careful because you guys are much more careful than I am. Okay, so I'm going to rewrite this bit out super carefully. Yeah. So it should be 30 times 100 minus 92.2, which I am just going to do because that is a much better idea. So that would be 7.8 minus x. And that makes much more sense, doesn't it? So we've still got all of that the same, but we should have 30 times 7.8, which is 234 minus 30x. And then all of that should end up divided by 100 because it's abundance, but it's not fitting, is equal to 28.109. And then I'm going to times that by 100, and I don't have space. They all add to make 100. Yes, they do, guys. Yeah. So we've got 28.109 times 100. I'm just going to do that over here because there's not space. Is 2810.9. Was Cricket Ray. Should we be misusing X, not adding? So thank you, Hazel, for explaining that. So right now I'm just rearranging this. So if you guys should also be doing this. This is one hella difficult question. So with questions like these, it's sort of seeing them lots of times that helps. So if you see them lots of times, you won't make mistakes like I just did. 0.6. So right now, that's the question. All right, I'm going to need to like get rid of some of this stuff on my screen because it's all getting a little bit messy, isn't it? So I'm going to put this up here. And once I've minused all of these, and keep in mind, guys, I'm working on a phone calculator because I was silly and did not get a real calculator to sit next to me. So right now I'm getting minus 4.7 equals minus x, giving an abundance of 4.7%. But I want you guys to help me out and tell me if that's what you also got for the abundance. Did anybody also do this lovely question? Yeah. Is that Jazel saying yes? They also got 4.7? Hazel also got 4.7. Are these all yes, yes, yes? That's correct. Anyone else? Did anyone else take a stab at this? Okay, so what I'm going to do is really, really quickly run through how it was done for anybody. This was so no, honestly, it's my fault for not realizing that percentages add up to 100. That's definitely something your chemistry teacher should know. So you're okay, but we should have, when something looks about right, if something's gone wrong, it's probably that it's gone wrong in your calculator. So what I'm going to do is really quickly run through how we did it. And then you guys should all have it. So the question was the molecular mass, or sorry, the relative atomic mass of silicon is 28.109, and we were given just that silicon 28 is 92.2%, and we weren't given 29 or silicon 30, which means that we wanted to know this one, so we called it X. And then very helpfully, somebody reminded me that if we did 100 minus 92.2 plus X, we would have silicon 30, which means that we only have one unknown, the X, which means that we can use our formula for relative atomic mass to figure out what the abundance of silicon is. And the formula for relative atomic mass is all of the masses times their abundance over 100 is equal to the relative atomic mass, which means that what we needed to do was do our 92.2, which is the abundance of silicon 28 times 28, plus X times 29, because X is the thing we want to know, plus 100 minus 92.2 plus X in brackets times 30, divided by 100 equal to 28.109, and then we just rearrange this for X. Does that make sense for everyone? And we got 4.7%. Does that all making sense? Have we stopped listening? Does it make sense, people? Yes. Okay. So if there are no other questions, then guys, I'm going to leave it there and you guys can just keep commenting and things. So it's been really lovely. Thank you for being here and showing up. You're welcome, Cricket Ray, still listening. Arlen, I can't answer random questions from random parts of the syllabus. There will be a web class on acids and bases. So I'm going to say goodbye. Have a lovely evening. And I hope that you have a nice rest of your week.